session is particular about green buildings. So after sustainable landscape design, we would like to talk about energy efficiency. You know, any green building which has the utmost importance, that's energy. We have importance for water and waste, other aspects, but especially the commercial building, energy efficiency is very, very important component. So with this, I would like to invite our next speaker, Dr. Architect. He's a doctor as well as architect, Mr. Amit Hajela from NEEV Architects. He will be speaking on mixed mode design for energy efficiency. He's there? Yes, sir, please. So I would like to just introduce before you set the stage and give you a presentation. Dr. Amit Hajela is an architect and urban design involved in the professional practice and consultancy since last 27 years in the disciplines of architecture, interior, and urban design, having designed and executed over 150 projects. Besides his academic association and research contributions, he is a fellow of the Indian Institute of Architects, fellow and founding member of Institute of Urban Designers, India, a member of Indian Institute of Interior Designers and various other professional bodies and membership associations. Thank you very much, sir. So stage is yours. So just audience is waiting for your thought process. Thank you so much.
So good afternoon, friends. It's a pleasure to be here this afternoon. And thank you, Madhu, for making my job easier because he had shown some wonderful projects. But I have deliberately chosen not to talk projects, but to talk about an approach. And an approach which probably we feel is important with respect to energy conservation. For the last 2 days, a lot of speakers have already spoken about various aspects of sustainable design. But here I would like to talk to you about the mixed mode strategy as an approach to sustainable design. Now, over the years, we have seen that about 50% of the estimated energy consumption goes into buildings. That's a larger global estimate in terms of energy consumption.
Check.
And besides that, we also understand that the energy demand with respect to buildings comes substantially from the HVAC component, which is almost about 60 to 65% of the total energy demand being consumed by any building. Therefore, if we have to make a significant impact onto the total energy consumption in a building, we probably need to look at HVAC very, very carefully. With that, probably there is an opportunity to go into a mixed mode approach, which basically is a hybrid approach to space conditioning that is a combination of natural ventilation and openable windows, which is either manually operated or automated, and the mechanical systems that provide distribution in some form of cooling. Now, with the kind of the cooling demands that we have, particularly with respect to the air quality and the indoor air quality, it is becoming imperative to go into some form of cooling and provide the right kind of thermal comfort conditions, at the same time addressing the requirements of quality of the air inside the building. Most buildings which are heavily dependent on air conditioning do have an impact which we also call as the sick building syndrome. And that's probably where you need to pump in a lot of fresh air to probably get the right kind of a mix of the indoor air quality. And therefore, here is an opportunity where we try to mix the ventilation, natural ventilation systems as part of the air conditioning system, and marry the passive and the active part of the design together. Now, well-designed mixed mode building allows spaces to be naturally ventilated, and during periods of the day or the year, I mean, it is all voluntary, I mean, the way it could be designed with respect to the quality of air that is available, and the quantum of energy that could be utilized through these mixed mode systems. which can be supplemented, is critical. Of course, the goal fundamentally is to maximize comfort and provide comfort conditions by minimizing the total energy demand on the buildings. Now, if we were to classify some of these buildings into the mixed mode buildings, basically we can classify them into three types of mixed mode design systems. One is a concurrent system where mechanical cooling and natural ventilation operate at the same time and at the same space. That means it happens together, it is in tandem. The second is a changeover kind of mixed mode system where building switches between mechanical cooling and natural ventilation on a seasonal or a daily basis. And the third is the zoned system where the mechanical cooling or natural ventilation operate in different areas of building as per requirement. Now here what is important is that while we engage in some kind of building design, it's important that we strategize the entire integration of technology that we propose to integrate with the building design right from the design stage itself. So in case there is a strategy to address a building, therefore we need to identify the right kind of appropriate technologies that will go into the adaptation for the design of building, and in many ways it informs the design and the way the implications it has in terms of the requirement of energy and the kind of different alternative technologies which could be mixed together to get better energy efficiency. Now, what are the benefits of the mixed mode systems? One, it reduces the energy consumption, reduces the CO2 emissions, improved occupant comfort, improved indoor air quality and occupant health, greater degree of personal control, connection with nature and in the environment, and lower operating cost. Now, studies have shown that there are huge components in terms of the OPEX, which comes as a consequence of the operations of a building over a 10-year period. It has been identified through multiple researches that after a 10-year period, the OPEX increases many times the CAPEX. So therefore, the impact, if it has to be drawn, has to be on the OPEX side of the building, and probably that is what contributes immensely. Now, if we were to look at the comparative characteristics of the buildings, one which is with natural ventilation, air conditioned, and a mixed mode building. So how does this impact the building form? Normally, the naturally ventilated spaces would be narrow floor plates with cross ventilation and with reasonably generous ceiling heights. However, with most air conditioning buildings coming in, we have large floor plates, relatively low ceiling heights, and often preferred because we reduce the volume and therefore we improve the efficiency of the air conditioning system. However, in a mixed mode system, we would probably get a planned depth of about 15 meters, which is desirable for the kind of natural ventilation to be adapted. And we take full advantage of natural ventilation along with the active systems of the HVAC. Now, the second component is the building envelope. The mass of the building is critical, and the thermal mass that actually is embodied is critical, and probably we design for different climatic zones in different ways. And therefore, the mass of the structure helps to dampen the diurnal temperature swings, and this external shading is an important factor by which we could reduce the insolation that gets absorbed into the building. Now, most of the air-conditioned buildings that we see, that the envelope is usually lightweight, usually glass buildings that we see, phenomenal use of glass, whether there's tinted glasses, high-performance glasses, and relatively less investment into external shading. And probably that brings in a lot of solar radiation into the building, having direct impacts on the total air conditioning load of the building. So the solar gain is reasonably high. However, in a mixed mode, we use the performance of the thermal mass of the building. We can dampen the daily temperature swings, and external shading is preferred. So if we mix these passive techniques and right kind of shading devices, we could actually reduce the solar gain in the building. Now, the critical component is with respect to the windows and lighting. Now, in case of windows with respect to quality, we have the relatively small openings depending on the climatic condition that we have in various parts of the country. But in case of air conditioning buildings, we usually end up having very sealed systems, which is the entire envelope is sealed, and it is dependent because any kind of infiltration would add up to the air conditioning losses. However, here in the mixed mode system, we still have an advantage of having both the automatic and manual control of opening of the vents, and the air conditioning system then supports, and then we minimize the total demand on the energy. Now let's see what happens. I mean, even when we talk so much about it, what are the limitations of the mixed mode system? Mixed mode would always have a site-specific limitation in terms of its application. Usually there is lack of predictability in this case because thermal conditions and ventilation rates differ in various climatic zones in the country. There are environmental trade-offs as well, which particularly are connected to noise, security, cleanliness, and the level of pollution. Of course, we have the building codes, which talk about the ventilation, the quantum of ventilation. The ECBC code talks very clearly about all these things. But sometimes also the unfamiliarity with the design codes and also with the design techniques and approaches of mixing the right kind of technology also translates into the limitations for a mixed mode system. Fundamentally, we were told, and I mean, of course, a lot of studies have shown that any kind of investment in green buildings does not cross about 1.5 to 3%. So therefore, getting into a mechanism which is a mixed mode system of design, which probably would not have a very potentially high cost to begin with. But then over a life cycle of the building, this can be easily recovered, and probably it supports a lot of reduction in the operational cost and the energy demand. Now I'll just give you a very quick overview as to how mixed mode can be applied to different climatic zones in the country, and what are the right kind of technologies which probably can go as part of the mixed mode approach to design. Now we have 5 climatic zones which have been very clearly defined by the ECBC. So on the basis of that, I've tried to put this together. For the cold climate conditions, the mixed mode adaptation could be in terms of gas-fired boilers, hydronic in-floor slab radiant heat, and clear-story windows that bring in a lot of solar heat, and the solariums and probably are more useful in those kind of climatic conditions. Stack ventilation effect does help. And in this case, we use ceiling fans primarily to improve the draft inside the space. For moderate climate, particularly areas of Bangalore or Pune that we have, enthalpy wheel works very well in these kind of conditions. The GSP and the ceiling valence convectors for heating and cooling are a good practice for application. Operable windows, again, would enhance because with respect to the climatic conditions, the temperature, the wind, you can change the mode of operations and the quantum of fresh air which could be brought into the system. User controlled temperature, because here we adapt to the climate, so therefore user controlled temperature is important. In case of cold and sunny climates, particularly areas of Leh, where we have this kind of climatic types, trombe walls are an important strategy that could be deployed, along with the electrical radiant ceiling panels, with passive solar gains and direct evaporative cooling towers and downdraft ventilation. Composite climate, by and large, the substantial area of the country is being covered under the composite climate. So here probably we could be looking in terms of an air conditioning which could be a shared chiller loop. We could be looking at naturally ventilated spaces with heating interlocks, cool night temperature and captured UFAD system released during the day, and high exhaust vents are an important component of this mixed mode. Of course, the direct evaporative cooling systems with downdraft ventilation is another method besides applying radiant floors and radiant cooling systems, radiant panels, and also investing into night evaporation. That means we also use ventilation during the night to cool the buildings. This all can be controlled through the building energy management system. So we deploy a building energy management system which can help us to identify this quantum of input. Now the kind of warm humid climates that we have. So the opportunity here is to use a ground source heat pump with desiccant dehumidification, which is an absolute requirement. The temperature and humidity sensors, which could be integrated to the building design and again connected to the building energy management systems. The mechanical system could probably use the ground source heat pump for heating and cooling, enthalpy wheels. Again, operable windows, manual or automated. Radiant floors, passive solar heating, decentralized HVAC systems, energy recovery ventilators, and automatic windows, which probably could be done in conjunction with the stack effect. Hot and dry, again, this is a very significant component, where we have zoned and naturally ventilated systems, operable windows, underfloor air, chillers, operable windows again, and we could probably be using the right kind of VAVs as part of the system, and this could be used for the night backboard effect, could be integrated with the windows. Chilled beams are again a solution to this kind of situation where you could integrate it again with the radiant floors. Of course, in a lot of warm, humid conditions, the issue of condensation is important, which needs to be very carefully calibrated and integrated to prevent excessive condensation in case of humid conditions. Now, fundamentally, what could be the mixed mode strategies that we could put together? Natural ventilation during working hours can be alternative with an alternative system with active system and peak conditions that could be worked out. Night convecting cooling strategy is critical, where we allow natural ventilation outside the occupied hours. The combined effect of evaporative cooling, which is important. A moisture pad in an air handler would again add to it. Then radiant cooling elements coupled with cooling towers, indirect evaporative cooling. And then in climates where it supports, we could use the standard borehole heat exchangers, that means the earth-air tunnels, which could be provided. Arid regions, the kind of outcomes and the analysis that we have in terms of numbers is that simply operating conventional active systems with mixed mode can bring about 51 to 63% reduction in the energy consumption through a mixed mode strategy. And that is particularly for office buildings. And in case we are implementing it with radiant cooling, we can top it up with another 12% in areas which are particularly in the arid zones. Now, in case you adopt the night ventilation, which as integral part of design, we can bring the energy demand between 62 to 78% for one system and between 70 to 79 for systems with low heat gain cases and 63 to 71 for high heat gain cases. Now, in case we invest into direct evaporative cooling, we can save up to 20%. And if we use a cooling tower to reject heat and a slab radiant cooling system, then it will translate into about 17% reduction in savings and up to 25% by using the combination of this mixed mode system. So the greatest savings that can be accrued in less humid conditions, and the plant energy savings can be as high as 55 to 73%. In case we use borehole heat exchangers, again, you can top it up something between 12 to 25% of the total heat gain. And an overall plant energy savings can be brought down within a range of 51 to 72%. Now, a study is done for an average 3-story office building for a composite climate. During winters, this building can be actually operated on simple natural ventilation system during office hours. You don't need any kind of active system to support it. However, in summer, air conditioning is used as necessary for maintaining the right kind of thermal comfort. So the final achieved mixed mode during these two processes, overall, on an annual assumption, can bring down the energy consumption by about 55% overall. However, by doing so, you can still get better views by having large windows, and it works to the advantage even with respect to daylighting. So you could do a proper integration of building management systems by putting the CO2 sensors, by putting the lighting sensors, and then you could actually operate the mixed mode system using a manual mode or an automated mode, depending on the cost and the budgets available to you for a particular design of building, and it could be put to right kind of application. Now, fundamentally, if you say take a baseline case, we will be able to use about 30% of natural ventilation into the whole system, which is more useful. I'll give you a small case which was being deployed in the Liberty Tower at Meiji University in Tokyo, where they created a wind floor on the 18th level. And they had the roof gardens, and the central core of the building was designed to operate on a simple stack effect. So we get the air which was being drawn from the periphery, and through the stack effect, the air would move up and would be released out at the 18th floor. Now, since the 18th floor had openings on all 4 slides, it didn't have any impact on the nature of the wind flow and the quantum of wind flow that happens. So that contributed tremendously into the right kind of demand of integrating the natural ventilation. And in many ways, natural ventilation integration could probably give the right kind of opportunities also in some other intangible ways, where probably the requisite amount of ventilation could contribute to the compartmentation component of the fire safety, where you are able to release the smoke out in case of a fire if it erupts in a particular envelope and if it is being compartmentalized. So therefore, there is a great opportunity of integrating the natural ventilation systems into our buildings. Now, to conclude, I'll just give you a simple methodology for doing this kind of thing. I mean, the fundamental is to do a climate analysis. You need to know the space use and the furniture layout, which has to be done. Setting up a right base model, which is a mix in terms of the mixed mode strategy for the quantum of natural ventilation and the active systems using an HVAC system. Incremental and integrated building design. I mean, the approach has to be a comprehensive, holistic approach where you use to full efficiency the passive side and the active side of the building and optimizing the total energy demand in a building as a whole. Naturally ventilated, robust building design is probably the key to energy conservation, and mixed mode building design is probably a way forward that we look forward to design of buildings in India and kind of the energy demand and the resources that we have to our command. Probably I see a great opportunity where we look at these alternative systems and try and mix them and take full advantage of each technology that is being adopted. So the bottom line is to strategize the building. It is not only that the aesthetics that we talk about a building, but how well a building performs over its life cycle, and the way we can optimize the capital and maybe take advantage or maybe utilize the capital investment and reduce the operational expenditure over the life cycle cost. Thank you very much.
Hello, hello. Yeah, it's working now. Thank you so much, sir, for such a, you just be here. We want to felicitate and just some questions from the audience we would like to take. So after this wonderful presentation, hello, which shows you that how to optimize your building envelope when you design a building, and how the mixed mode design is very important to achieve the energy efficiency. So I would like to just open the floor for discussion. So any question from the audience, from our eminent speaker, please just come and you can interact with the panelist, please. Anyone from the audience? Yeah, you need a mic.
Yeah, I'm Suvarna from Meta Design. I just wanted to ask you regarding this, sir, enthalpy wheel. Can you just elaborate a little bit on the enthalpy wheel and how we use it on the in the mixed mode?
utilized these days. And of course, this is a response to the climatic condition in which this application is more adaptable. Of course, it demands a lot of detailed calculations to do that. So I would fall short of not going into those details of talking about the technology that goes into the design of enthalpy wheel. But it finds a great application, and it contributes immensely to the reduction of the energy demand using that technology and integrating as a part of the mixed mode system.
It is the part of the air conditioning plant
Yes,
itself?
yes, that's right. That's right.
Any other question from the audience? Sir, I would like to have a question from you regarding radiant cooling. So,
Yes.
will you just tell me how radiant cooling is better than any conventional technology, and how much energy efficiency we achieve when we design our building by using this technology?
Okay.
Yeah.
See, radiant cooling systems are very effective, particularly in composite climates and hot, dry climates.
Can you take the mic just-
When you put a system of network of pipes and they're embedded into the ceiling, you run water into that. And again, it has a great component of sustainability where you could probably use the recycled water into the system. The fact is that we know that the maximum heat transfer in any building happens from the roof. So therefore, if you're able to reduce the temperature at the roof level by running in these pipes and bringing down the total energy or the heat which is being absorbed, it will actually bring down the heat transfer onto the envelope. When you reduce the heat transfer on the envelope, the demand side on the energy will automatically go down. So it becomes a very effective tool. Yes, the careful aspect of design, as I said very clearly, when the relative humidity is high, you have to control the component of condensation within the pipes, which probably might lead to dampness into the slab. But effectively, if it is being designed and operated well, it is a very, very effective tool to bring down the total energy demand for air conditioning on the active side.
So, we could expect 30 to 40% energy saving?
Absolutely, we can expect something to that tune. And I think one of the finest example of this radiant cooling as a test case, you could look at the Irad building, which has been done in Gurgaon. So the Irad building uses the combination of radiant cooling, and there they have been able to reduce the energy demand by almost about 30% by using radiant cooling.
Thank you so much for such wonderful presentation and giving your knowledge insight to everyone. I would like to call upon again my chair and co-chair, Hitenji, both of you, just to felicitate our speaker. Green anchor. Is Amit Hajela. Amit Hajela. Thank you so much.